For this section, we're going to be looking at solving differential equations by using series methods, and it's not exactly the most fun way to solve a differential equation. In fact, if I had my choice, I would rather go with separation of variables, the characteristic root equation, method of undetermined coefficients, if the equation happens to be non-homogeneous, and even if it were homogeneous, I would still prefer other techniques. And just referencing what we have dealt with in series, and these are some of the summation representations of what we have with commonly used functions. We have e to the x, and again, just like the Maclaurin series, you have 1 plus x squared over 2 factorial, and so on. And in summation terms, we have this to be the sum of x to the n over n factorial as n goes from 0 to infinity. And you have also summations, okay, for cosine of x, sine of x, as well as the hyperbolic cosine and sine of x. And we also have, again, other functions like the natural logarithm of the quantity of 1 plus x and 1 over 1 minus x. And we also have like a representation of what we have with the power series. Okay, and looking at solving differential equations by using series and summations, and we have as the general model, okay, where summations are concerned with x as the independent variable and y as the dependent. So we have y is equal to the summation as n goes from 0 to infinity of c sub n times x to the n, and the expanded notation, and we are going up one whole number at a time, so we have c sub 0, and you have c sub 1 times x to the first plus c sub 2 times x to the second. And we have with the subsequent terms, you're going to have a match in the values between what we have subscripted in the letter c and superscripted in x. And now if I take the first order derivative, notice that you're going to have the constant c naught is going to go out, while we have c sub 1 times x, the derivative goes to c sub 1, c sub 2 x squared goes to 2 times c sub 2 times x, and we have c sub 3 x cubed, okay, it's going to be 3 times c sub 3 times x squared. Okay, notice that we have a change up in terms of the value of the leading coefficients before the representations of the general constants that we have in the subscripted c's. Okay, instead of just having 1 throughout, we got 1, 2, 3, 4, 5, 6. And we have no longer a match between the subscripted value and the power value to which x is raised. And we have in the rewrite for the compact summation representation, with the fact that c sub 0 is out, we're going to have the first order derivative to be the summation as n goes from 1 to infinity, since we have c sub 1 to be the constant with the smallest subscripted value. And for the rest of the terms, okay, the derivative of c sub n x to the n goes to n times c sub n times x to the n minus 1. So we're using the power property of derivatives. And if I were to use this again, okay, we're going to have n times n minus 1 times c sub n times x to the n minus 2. And this is going to be the statement in general terms for what we have in the summation of the second order derivative. And notice in the layout, c sub 0 went out, c sub 1 now goes out, and the minimum subscripted value is going to be at 2. So we have n going from 2 to infinity. And so we have in the expanded notation, we have 2 c sub 2 plus 6 c sub 3 x, and so on. And if we take what we have in the series, okay, and say that we look at solving first order differential equations by using series methods, and we can say just as a start, okay, something foundational yet basic yet complex, we have y prime plus y is equal to 0. Okay, now, so just taking what we have for y prime in the series expansion as well as y. Okay, and so we got, again, so you have c sub 1, 2 c sub 2 x, and for y we have c naught, c sub 1 x, and so on. And looking at mapping together okay, the terms that had the same degree in x. Notice we have from y prime, we have the constant at c sub 1. From y, we have c naught. And if we pair these up, okay, you have like c sub 1 plus c sub 0 is equal to 0. And taking what we have with our first order x terms, but just taking the constant portions. So you have like 2c sub 2 times x plus c sub 1 times x is equal to 0. And if I just fixate on just the constant portion and not worry about the variable x, so you got 2c sub 2 plus c sub 1 is equal to 0. And then we have, for the constants designated alongside the x squared from both series sets, we have 3c sub 3 plus c sub 2, set that equal to 0. And third order we have 4c sub 4 plus c sub 3. Again, fourth order we have 5c sub 5 plus c sub 4. Okay, and that arrangement is going where we have a system of equations set equal to 0. And I'm going to try to set each of the natural number subscripted constants in terms of c naught. Okay, so we have from the first, we have c sub 1 is equal to the negative of c naught. And for 2c sub 2 plus c sub 1 equal to 0, what I'm going to have here is that 2c sub 2 is equal to negative c sub 1. In turn, c sub 2 is equal to negative 1/2 of c sub 1. And with c sub 1 at negative c naught, you want to have c sub 2 equal to negative 1/2 of the negative of c naught. And for 3c sub 3 plus c sub 2 equal to 0, we have with the subtraction and the division that follows, we're going to have c sub 3 equal to negative 1/3 of c sub 2. And just clustering together, we're going to have c sub 3 is going to be equal to negative 1/3 of negative 1/2 of negative c naught. And for c sub 4, you're going to have like negative 1/4 of negative 1/3 of negative 1/2 of negative c naught. And you're just going to have, again, clustering, like c sub 5, you have negative 1/5 of the previous statement. And like c sub 6 would be like negative 1/6 of that. And again, so you're going to have a bit of clustering that is going to follow. And just looking at what we have in the pattern. So we have c sub 1 equal to negative c naught. Okay, and so we have c sub 1 is equal to negative 1 to the first c naught. C sub 2, okay, that's going to translate to a negative times a negative, where we have like negative 1 to the second c naught all over 2. For c sub 3, we have negative 1 to the third c naught all over 6. And we have with c sub 4, we have negative 1 to the 4th c naught over 24. And for c sub 5, we have negative 1 to the 5th c naught over 120. And if you notice, you have a match between the subscripted values and the degrees to which negative 1 is raised. And for the significance that 2, 6, 24, and 120 will play, well, those are factorial values respectively. What we have for the factorials are 1, 2, 3, 4, and 5. You notice the degrees to which negative 1 is raised, and what we're taking the factorial of in this symbolic notation matches what we have in the subscripted value for each of the respective constants. So we can say that for any natural number n, we can say we have c sub n is equal to negative 1 to the n over n factorial times c naught. And going back to what we have for the general representation of what we have for y, again, we have n from 0 to infinity, you have c sub n times x to the n, and replacing c sub n with its equivalent from the set. So you have negative 1 to the n, c naught over n factorial, and you have times x to the n. Now we're going to shift c naught on the outside, and we're going to cluster together negative 1 to the n times x to the n. And if we sandwich together, we're going to have negative x to the n, and you have all over n factorial. And looking at referencing what we have, say, from your textbook, in the case of the series representations, well, guess what? We have e to the x is equal to the summation as n goes from 0 to infinity of x to the n over n factorial. And we have almost the very same thing, except what we have raised to the nth power is going to be negative x. And guess what? That will be referencing e to the negative x. And guess what? So we have in the follow through. So we have a constant times the summation as n goes from 0 to infinity of negative x raised to the nth power all over n factorial, and that will translate to c naught times e to the negative x. Right. And another case, and let's say that if I have y prime minus 4y is equal to 0. Okay, and for what we're going to have here, a lot of the same stuff. You still have the y prime, and you're going to have the y all over again, but each of the series terms that we have from y will be multiplied by negative 4. And so if we map together like we did with c sub 1 and c naught, well, this time we'll have c sub 1 minus 4, c naught is equal to 0, and do likewise 2c sub 2 minus 4c sub 1, 3c sub 3, 4c sub 4, 5c sub 5, minus 4 times the c sub 1 less than what we have subscripted in the leading term. So you're going to have a pattern where you have c sub 1 is equal to 4c naught, and we have for c sub 2, that is going to be 4 halves of c sub 1, and just clustering together, that's going to be 4 halves of 4c naught, and for c sub 3, that's going to be 4 thirds of 4 halves of 4c naught, and we have c sub 4, you got 4 fourths of 4 thirds, 4 halves of 4c naught, and so on. And c sub 5, you got 4 fifths of what we have in the previous line. And just looking at taking what we have in the arrangement. Okay, so you know, have with c sub 1, you have 4 to the first c naught, c sub 2, 4 squared over 2 c naught, c of 3, we have 4 cubed over 6 c naught, and so on. And putting the denominators in factorial notation, again, so you have c sub 1 will be 4 over 1 factorial c naught, c sub 2 you have 4 squared over 2 factorial c naught. And if we go all the way down, you're going to have a pattern where we have c sub n is equal to 4 to the n all over n factorial, where we have that ratio multiplied by c naught, and relegating what we have for y. Okay, so again, we have y is equal to c sub n times x to the n as n goes from 0 to infinity. And looking at what we have for c sub n, again, we have 4 to the n times c naught all over n factorial. And then we have times x to the n. And again, if we shift c naught to the front and cluster together 4 and x, since both of these factors are raised to the nth power, consolidated, we have 4x quantity to the nth power over n factorial. And if you notice, okay, we have a base to the n power over n factorial. And guess what? You're going to have this summation part is going to be referencing what we have for e raised to the 4x. Okay, so we have in summation terms, we have the constant c naught times the summation as n goes from 0 to infinity of the quantity of 4x to the nth all over n factorial. And this will be equal to c naught times e raised to the 4x. Now for one that's a little bit tricky, say we have y prime minus 4x squared y is equal to 0. So I'm duplicating what I have with the series expanded from y prime as well as y. But in y, each of the terms will be multiplied by negative 4x squared. And if I were to itemize, okay, notice that c sub 1 is the only constant, and 2c sub 2x is the only term that we have that is first order in x. Okay, and as I look into the squares, you have 3c sub 3 minus 4c naught. So you have the first pairing between c sub 3 and c naught. And then for the rest, you can have a bit of a cycle. Well, since c sub 1 is the only constant, that is going to be 0. And guess what? That's going to carry over to anything that pairs up with c sub 1 and spins off from that. So like c sub 1 is paired up with c sub 4, but since c sub 1 is already 0 because it was the only constant, you're going to be going every 3 constants, so to speak, where c sub 1 is equal to c sub 4, 7, 10, 13, and so on. And those subscripted constants will be equal to 0. And because we have c sub 2 as part of the coefficient of our only first order x term that exists. Okay, c sub 2 goes to 0, and anything that pairs up with it and spins off from that is going to go to 0. So we have like c sub 2, 5, 8, 11, 14, all those will go to 0. But for what we have in the mix-up, okay, so we have 3 c sub 3 minus 4, c naught is equal to 0, and putting c sub 3 in terms of c naught, well, we have c sub 3 is equal to 4/3 of c naught, and we have pairing up what we have with c sub 3, we have 6 c sub 6 equal to 4 c sub 3, and c sub 6 in terms of c naught will be 4/6 of 4/3 of c naught, and go every three constants. So we have c sub 9, that'll be 4/9, so 4/6 of 4/3 of c naught. And just putting this in terms of sort of the familiar zone with factorial notation. Okay, now we got c of sub 3 equal to 4/3 of c naught, and if I want to put this in terms of 1 in the denominator, well, 4 over 3 will be 4/3 over 1, so we can say we have 4/3 to the first over 1 c naught. And for c sub 6, well, guess what? If I want to write the 4/6 in terms of 4/3, well, 4/6 is going to be 1/2 of 4/3, and that of 4/3 over 1 c naught. Guess what? I have 4/3 times 4/3, and half of that c naught. And for c sub 9, well, guess what? You have 4/9 jutting out at the front, and 4/9 would be 1/3 of 4/3, and clustering what we had in the conclusion of the second line, we're going to have 4/3 times itself all over 6 c naught. Okay, yeah, a lot of crowding that is going on, but if you notice a pattern, you will have c sub 3 is equal to 4/3 to the first all over 1 factorial c naught, c sub 6, okay, with 2 at the bottom and 4/3 repeating once, so you have 4/3 square c naught all over 2 factorial. And for c sub 9, you have 4/3 to the third c naught all over 6, which we have with 3 factorial. And if you notice, okay, the power to which 4/3 is raised, as well as the value that we are taking the factorial of, will be 1/3 of what we have subscripted for c on the left. So you have a bit of a pattern where we have c sub n is equal to 4/3 raised to the n over 3 power c naught, and we have all over the factorial of n/3. But let's say that if I want to make the fraction such that we have integers, and if I just undo the thirds multiplying by 3, and say if I let n be equal to 3k, well, in the rewrite we're going to have c sub 3k is equal to 4/3 to the k c naught all over k factorial. And guess what we have for y? Again, your introductory definition we have is n goes from 0 to infinity of c sub nx to the n, and that is equal to putting in terms of k, letting n be equal to 3k. All right, so we have c sub 3k times x to the 3k as k goes from 0 to infinity, and replacing c sub 3k with what we have in defining that constant arrangement. And so we're going to have 4/3 to the k c naught over k factorial times x to the 3k, and shifting the constant to the front and clustering together 4/3 to the k and x to the 3k, and we have with the power properties of exponents, they have 4/3 to the k times x to the 3k, and now 4/3 is to the k, but now for x to the 3k, I can say that that is going to be x cubed raised to the k, and I can cluster together 4/3 and x cubed, where 4/3 to the k times x to the 3k can be expressed as 4/3 of x cubed raised to the k power. And putting that all together, you have c naught times the summation of 4/3 x cubed to the k over k factorial. And so this would be another reference to e to the x, where we have in terms of k, we have as k goes from 0 to infinity, we have e to the x equals the summation of x to the k over k factorial. And for what we have in the set representing x to the k, we have 4/3 x cubed quantity to the k over k factorial. and we have that will be the summation counterpart with what we have with c naught times e to the 4/3 of x cubed.